Test, test. Hello YouTube. I am going to do a 4-bit computer tutorial based on a viewers' request. And yeah, this is part 1 of it. So we're going to start off with the ALU, of course, because it's quite possibly one of the most important parts. And well, I guess that's what I'll make first. So yeah, ALU. So I'm going to make the ALU, and basically what an ALU does is it adds. So let's say you have two numbers. Well, you can add them in the ALU, you can subtract them, and since they're in binary, crap, you can't type and talk. Never mind. Since they're in binary, you can also do logical operations on them, like AND or XOR, and so on. So an ALU has 3 inputs, an A, B, and an opcode, and I just usually shorten that to O. So for output, well, it's obviously going to need to be 4 bits, and I'm just going to label it output because why not? And I always prefer to have a reset pin. The reason I'm not having a pin for A, B, and O, as I've done in my 4-bit computer previously, is because I want to also include the registers in here, which I think would be better. So we're going to start off with these registers. So what a register does is it saves a bit of memory temporarily. And that sounds pretty simple, but they're really important because a lot of times you need to save something temporarily in computers, like let's say you're doing Fibonacci sequence, but you need to save your last number. Well, of course, you want to save it temporarily because it's much more efficient than saving it every single time. It's a little late at night because night time's really the only time I have time to do free stuff like this. So yeah, I'm a bit tired. So anyways, here what I've done is I've wired each of them set pins that I just mentioned to a reset pin. And I've wired each of them set pins to a clock pin. And upon doing so, that allows you to, of course, set the values. You gotta make sure to set these to 4-bit registers, obviously. So that's our registry system. And for labeling purposes, I want to put this as A. Okay, who cares? It's a pain in the butt. I hate Logisim's labels, so annoying. So we got all of them. So what we need to do is we need to link these up in buses. So we'll have a big bus here. Now basically a bus is just a group of wires that carries a bit of data. So this bit of data will tell the compute will be what we perform operations on. So to perform an operation, I'm going to start with basic operations, and let's fix our gates here because nobody uses 5 input gates, and nobody wants giant looking gates. So for each of these, I'm just going to set down the 2 inputs and narrow. I could think it's fairly stupid, but you have such big gates. Okay, so anyways, we're going to have some basic operations, and we're going to start these out from pass A, pass B, which is fairly useful, and then some not A and not B. So we'll just duplicate them. And if you're wondering what key presses I'm using Control-C to copy and Control-V to paste. We'll set that to not 2 to 4 bits. And we'll just do this for each. We also need to make sure to set the knots. And after we get done, we'll do something most people wouldn't consider very important, but do something important, is going through each of these and setting the audio and stuff. A, B, where's our gates again? I was. Set that to narrow, number of inputs 2. each of these. And now for XOR, which is used in adding. Now technically this can be used to add in stuff right now as it is, and we don't need to add any more logical operations. But I think that's kind of stupid, because why would you only want like a couple of logical operations when, since we have a 4-bit opcode, we have a maximum amount of operations of 16. So why only limit ourselves? So we also need a multiplexer for our output. So we're going to make our output in 4-bit multiplexer. Now the reason for that is we also need to make it 4-bit data bits. The reason for that, is because our opcode is 4 bits. We also need to disable the enable pin. So for each of these, our first normal operation will be pass A, and we'll pass B, and then we'll pass not A, and pass not B. And that's useful for inverting things. And then we'll have AND, or XOR, so on. Now, we don't really need a NAND, NOR, and XNOR, because we can just take our output from OR and then send that to A, NOT it, and then send it to the whatever, graphics, whatever. I don't know what you want to send it to. So now that we've got that, let's go for some fun stuff. Arithmetic. So adding is pretty useful in computing because, well, it's pretty useful. I mean, everything comes from adding. Every single multiplication problem you have comes from adding. Now, an adder is made from an AND gate and an XOR gate as following. But Logisim has a feature where it already has that built into it. So I'm going to just, so this is a half adder. We provide the inputs, Oops. A. B. Sum. And lastly, our carryout. Wait, that's our carryout. What am I doing? So carryout. Now, what this does is, let's say we set our A to 1. Well, our sum is going to be 1. Well, since there is no 2 in binary, because a 2 would be a 1 and 0 in binary, you probably should know binary before watching this tutorial. When we set B to 1, it's going to give us 1, 0 as our output. If it's just 1, 0, it's going to be 0, 1. Or 0, 1, output's going to be 0, 1. 0, 0 plus 0, that's obviously 0. Let's fix that there. It's all bugged. Somehow I ended up making. Okay, anyways. So that's how whatever works. An adder works. So there's another form of adder called a full adder. This is only a half adder. It don't do nearly as much as a full adder. So here we have carryout and sum. So in the full adder, we have an extra variable, which is C, or your carry in. So we'll just rename it that carry in. So of course your carryout is still the same, but since this is Logisim, you can't route two outputs together, so we have to pass it through an OR gate. I don't think modern CPUs do that because you can just take 2 wires and connect them together like that, and if one's on and the other's off, it's not going to throw an error. Because real life don't really have errors. So let's run that. So carry in, we get 0, 1, 0, 1, 0, 1. Seems right. So carry in plus, so 1 plus 1 plus 0. Well, of course that's 2. Okay. 1 plus 1, 2. 1 plus 0 plus 1 plus 1. Well, 2 again. Now let's say 1 plus 1 plus 1. Boom, 3. So that's how a full adder works. So now let's say you want bigger numbers. So we'll take that. Oops, I didn't mean to do that. Let's give a little bit more space in here. Now, instead of our carry out and our carry in pins, we route our carry out from this one directly to the carry in of that. And what that does, I want this equal spacing here. Okay, sorry about my OCD. Now let's put this in a form that's more readable here. Because that's a little stupid how it be read. So that's a more appropriate form. And we'll rename our carry out to +1. And our carry in to +1. And we'll rename our carry out to overflow here. And so let's say we have, oops. I think I'm making a mistake. Okay, so we'll have our two A inputs here. Just so we can count this as normal binary instead of weird. So we can count this as normal binary, I guess. It's a term. There is a term. So here's our three inputs. We'll name this A1, A0. Actually, this is more like A1, and that's more like A2. And if this was 3 bits, the next one would be A4. Okay, so let's do. Actually, I don't like this. I'm really picky about this stuff. I'm really sorry. This bothers my OCD enormously bad. So, yeah, because I don't want to make it simple for you guys to read, but it annoys me because it's not like that. Okay, so here we go. Oh man, this is supposed to be a 1. So I put this in traditional binary text. So you know how you have two. Let's say for 4 bits you have 16. I mean, no, what am I doing? 8, 4, 2, 1. So this is 8. And this is 4. Yeah, I'm trying to lay it out like that. So we'll do 2, which is obviously 2, plus 2, 4. Okay? 2 plus 1, 3. Let's try 2 plus 2 plus 1, 5. 3 plus 1, 4. 3 plus 2, 5. 3 plus 3, 6. 3 plus 3 plus 1, 7. Pretty common sense stuff here. So that's how computers assign numbers. That's something fundamental you need to know, how a basic addition works. So here's that carry out and that carry in I was talking about. Now, we might use the carry out as a flag for I don't know what, or just send it out of the CPU. So we'll name this overflow. Now, since this is, one would argue a more advanced CPU than what I traditionally do, more advanced on the ALU scale, because normally I always have a lot of small logic operations that don't matter much. Well, I have multiplication too. Now, multiplication, when you multiply two numbers, let's take a calculator here. This calculator is crappy. Who even made it? Calculator.jar. Here we go. See, I made this myself, so this is better. See, look how much better this is, and this book crap. Who even made this? It's awful. The buttons aren't even outlined. See, here the buttons are very clearly. Okay, I'm done. So let's do 8 times 8. Now, obviously, anybody will tell you, right like that, that is not a 4-bit number. 64 is not 4-bit. If I'm not mistaken, 64 is 6-bit. So, obviously, we need a bigger than 1-bit carryout. So, let's do 15 times 15, 225. Now that, I can tell you straight off, is an 8-bit number. That's why your carryout is going to be, oh, I forgot you have to have this tool, that's stupid. Oh, never mind. It's going to be a 4-bit output. So what we can do is we could just route that with that. And it don't matter too much, honestly. And I should be able to view the contents of that. Yeah, it just zeroes out all of them. That's weird. That's probably some setting I have enabled. So, yeah. So now we got multiplication, addition. Pretty nice stuff. Now, bit addition. We could do that. Probably not. I don't know any good items. Let's do shift. Shifting. Because that's pretty useful. So we'll have logical right, logical left, stuff like that. Oops, I forgot to set the correct bit width. By the way, to select elements with the mouse cursor, you can press shift. So if I want to select that wire, then that wire, then that wire, so you can just hold down shift. Control C, copy, Control V, paste, and Control X, cut. So we want to shift A by bits B. At least try. So A by B. I don't know what I'm going to do for the 2 bits. Now, I forgot about, I have my plug in here. Yeah, here. So, luckily Logisim has these really nice splitters, which I love. So you can have a bit within a 4, and you can choose what bits to go through. So we will only let the first 2 bits in, and the other 2 will just ignore. So shift A by B makes pretty sense. I like it. So let's go in. Let's add that to the multiplexer. And if you don't know, a multiplexer just selects a bunch of inputs. So if you have 16 inputs coming in, it'll select one from the 16 and give you a certain output. Really useful. You use it all the time. You also have a demultiplexer, which has 1 input, and will send that 1 input to 16 different outputs. And you have a decoder, which, based on a binary value, will tell you the decimal representation. A priority encoder, which, if I'm not mistaken, based on the decimal input, it'll tell you the binary output. I'm not certain. And then you have a bit selector, which I've actually, I don't think I've used it. Data, data. Oh yeah, I know. I bet I know what it does. You basically have data in that selects a certain bit. So like if you have an 8-bit input, and it'll take a 3-bit. So let's say you have 2 inputs. Right here is your 8-bit input. Here's your 3-bit input. So your 3-bit input selects which bit that comes out here. Basically, like, the equivalent circuit here would be a decoder facing up. 3 bits, bottom left, yes. And a bunch of different buffers. So, boop. Boop. And basically a buffer here, all these little things I'm drawing out, they just decide, like, they're basically like a highway. They kind of decide what can go through and what can't. So let's say you want to limit a bit and you don't want it going to a certain part of the CPU. Well, you can just have a buffer that blocks it. Or you don't want something to trigger on the clock cycle, just have a buffer that gets rid of the clock cycle. Pretty simple. Of course, there's probably a better way of doing this, but this is basically what a bit selector does. I'm just trying to show you the example. I don't know if there's a way I can just pause OBS. If I did, but I don't really know if I don't know if it can. Probably can. Okay, that's just inconvenient. Who cares? Okay, next part. Boom. Yeah, this is much better. Where's the splitter? If you don't know, a splitter just splits an input. So, like, if you have an 8-bit input, it splits out into its bits. So, 0th bit, the first bit, so on. Normally, I'd just write a custom plugin to do this if I didn't know the bit selector was here, because it's much more convenient. Now you can see why the Logisim developer added this here. Now, as you can see, all these lines are red. There's a reason for that. It's because none of them are 0. Actually, not really. It's because buffers are 3-state, meaning that they can be in one of 3 states. Undefined. So, they could be undefined, on, or off at all times. So, here, let's put a buffer down. I'll have 2 inputs. So, this is input A. Here's input B. Here's output X. So, as you can see, right now, X is undefined. It's just showing an X. That's really it. If we turn that on 1, it's still undefined. If we turn that on, it goes to 0. Now, if we turn that on, it's 1. It's kind of like a lot like this, which is a transistor. Real computers, like a real CPU and a real computer, is just made of transistors. And they're fairly simple. So obviously this is a, what kind of transistor? P-type, yeah, here we go. Let's turn that to an N-type. So, as you can see, let me grab a buffer here so I can show you the massive difference between these two. Okay, so here I got a buffer and a transistor wired in the exact same order. So we're going to turn on the control pin. So boom. As you can see, they both zero themselves out. Now we're going to turn on that data pin. As you can see, it don't let it pass. But when we turn on the data pin, it lets it pass. So an N-type transistor is basically the same as a buffer. Now a P-type is basically a buffer with a NOT gate on it. So that's output and two inputs. So we'll turn that on, bang, it goes undefined. We turn that on, it's normal. But once we turn that on, it's undefined. As you can see, it don't act like, it acts like a buffer, but just with the top inverted. Actually, I think the icon changes. Yeah, see the icon changes there. So yeah, not sign. If you don't know a zero in front of something in computers means not. So we'll have our 8-bit input. We'll continue on our little thing about the bit selector, what it does. And this can be really useful in something like a GPU or a registry system. Trust me. So, okay. So here we go. Let me pull resistor all these. Basically, a pull resistor, if a value is undefined, it makes it 0 or 1. Can be changed. There we go. That was annoying me a little for some reason. So, this is what a bit selector does. I'll actually have a real bit selector, or at least this is, I'm almost certain this is what it does. Hover data in, selector bit. And our output bit. And we'll just put that right beside the pan. Okay, so we'll have an output of 1, 0, 1, 0, 1. And we're selecting the 0 with bit right now. At least I think we are, I'm not sure. Yeah, still a bit off. Yeah, I messed up my inputs. Nah, who cares? Okay, I probably should. Yeah, well, let's just put it 24. So, so what? You can waste 30 minutes with that. I'm evil. Okay, anyways, let me go to the next part. Divider. Yay. Boring. So, upper. Yeah, let's just not do that. That's probably going to be annoying. I don't really know a good one. Okay, we could do rotations. That's an actually useful way of, that's an actual useful operation that's used in our CPUs. So we'll have our A input. I know. Alright, yeah. And our B input. I forgot to cast it. Sorry, it's called casting. No Java. Where you like change one input to another input, I guess. That's not right, changing. So we'll take that, wire that out to that, and wire that to that. We get off track too much. Okay, and we need two more. Now, a lot of times I just do use constants because I think it's better than having to declare them in your program, since that takes up memory. And I think a lot of people would agree with me on that. And if you don't know, the reason I typed in F is because a Logisim does a lot of its things in hexadecimal. And you can use hexadecimal as a substitute for regular decimal. So that's our whole entire arithmetic logic unit as it is. Let's just even them powers out because they're bothering me. There we go. Okay, so now let's do the next part. Now the next part is called flags. Now flags are really useful because a flag lets you have if statements. So in coding you like to do like greater than, less than, equal to, stuff like that. More advanced stuff. So I think 3-bit flag input, or at least 2-bit. 2-bit's fine. 3-bit flag. That's probably our best option. Because I thought about 2-bit and I don't think that's good. So I usually like to do flags at the bottom of the CPU because it just seems better to me. But I feel that it's best to bus everything thoroughly. So we're going to use a comparator because, well, we're lazy. So if A is greater than B, and, well, you know. And since this computer is probably not going to be doing a lot with 2's complement, well, let's not use 2's complement. It's a little bit dumb. So we'll have our multiplexer, be our flag. Got 3-bit output. Now flags are always Boolean, meaning they're either true or false. And yeah, that's about all I can tell you about flags. They're either true or false. So we have greater than, equal to, less than, of course. Now we need to do some more logic here. This is why I hate flags, because however I end up doing it, it usually bothers my OCD. So now we have greater than or equal to and less than or equal to. Pretty useful. And one useful thing I use a lot in coding is not equal to, so might as well make that CPU addressable. And now for the regulars, which we all know is true. And, of course, false. Because where would coding be without true and false? I guess. I don't know. I was trying to make a cool analogy or whatever these things are called. Okay, so now that we got output overflow, now we can do flags. Yay. Or at least flag. It's not really a flag. Yeah, I'm gonna look at non-flag. So that is our arithmetic logic unit fully built. I kind of like to line up my output multiplexers like with each other for some reason. Okay, well, anyways, yeah, that should do it. I don't see any problems on this being pull up. And I do really like to pull all of our buses to 0 somewhere. And it don't really matter where you do it. Actually, I think it'd look better if I just do it like that. Do that. And there we go. So I like to pull all my buses to 0 because that prevents glitches. Yes, like multiplexing and stuff, I guess. So now we got all that done. Now we got our ALU done. Let's test it. This is the first one, and I'm probably not going to record it again because I'm lazy. So yeah, there's stuff about where I put it. Okay, there we go. That's about it. Start that up. Okay, anyways. Next part, testing. Yeah, good stuff. I forgot to make a separate circuit for this. You always need to make separate circuits. And so if you forget to make a separate circuit, just press Control A, Control X, and then Control V. And boom, there you go, separate circuit. So now what we're going to do here is we're going to have our arithmetic logic unit. Let's give it a nice little label here. That looks like a good label. And did I save? Yes. Project, load library. See, I've wrote my own libraries for Grant. I wrote my own libraries for Logisim, so yeah. Yeah, I'll load that up. Is that the beta build? I think this might be the beta build. Because I know the beta build crashes. I believe it is. I don't know where I'm going to put regular build. Oh, yeah. There we go, that'll work. So let's load that in. And yes, I have made this, and you will not be able to find it anywhere else. You can't tell me a lie. So, got my epic square LED. Really boring for people who are really boring. And I have not implemented label facing yet. So my labels do not have a facing. Because, well, I'm lazy. And then bring it binary to binary coded decimal item. And this converts any kind of binary to binary coded decimal. What on earth is on 8 bits? You can code it that. They're off. Anyways, where's our screens? Okay. One's place goes here, I think. And then the two's place. That's 10th. So now let's have an input system. 1, 2, 3, 4. Actually, never mind. I don't need to do that. Let's just open Fusion. File open recently. Wait, no, I'm already in that. That's open. I think I have one here. Here we go. Input unit. Oh, never mind. It's an IP input unit. Yeah. Here we go. Control A. Hey, you mouse work. So we'll have our input unit. Awesome name of ALU. Heck. Actually, that's doing crashing or whatever. It's Fixious. So, Logisim has this thing where you can edit the appearance of things and whatever. It's really nice. So, yeah, I always use it to my advantage. I kind of want to make this compatible with my plugin because, if I'm not mistaken, it crashes whenever you try to do it. And there's a circuit with my plugin in there. A little bit complicated when it comes to plugin making for this, because it seems like there's a lot of repetitive code. There we go. It seems better. One, 2, 4, 8, 7. I forgot I can't just do that. Yes, I'm biased towards my own LEDs. Another glitchy as crap. Hey, not my fault. I'm blaming Logisim for this. Okay, never mind. I'm not using them. They're awful. I need to fix them. there's our outputs. So I want 1, 2, 3, 8, R. So let's see. Why is there dot on it? A, B, and C. So our CMPM with that side, I'll be on set A, set B, and set O. Where's the pegs? After there. Let's see this will work. I doubt it. Logisim tends to be extraordinarily nitpicky about this crap. There we go. So that should allow only inputs if I'm not mistaken. I'm not sure though. So 1, never mind. Okay, that should do it. I think I'll buffer all these inputs since what's going to happen is one input's going to have a value and the OR decks are just going to track with it. Oh, I'm an idiot. Could do is I could just pass it all to a multiplexer slash demultiplexer. Oops, I forgot 4 bits. I'm going to disable the enable pin, and what we'll do is we'll just set a predefined value. Never mind. I don't like using buffers, but I'm afraid what's going to happen is it's going to do some weird timing thing, and Logisim has a tendency to do that. Sorry, I'm being a little bit mentally slow right now. I'm really tired. I decided to do this up at night where it's a lot less noisy. My family are pretty noisy people. I hope this going to rotate. Okay, never mind. But yeah, that seems like it'll work. So that's B, and that's our opcode. It's all going to our data ABO. Seems like it'll work. We set that to 4. Cement. Looks like we're having a bug here. We got numbers over first. That's easy fix. I know what our problem is. I don't know why I deleted them too, but I know what our problem is. It's the registries in the ALU. So, we pull up a square wave here. So right here, so this is a better graph. So here what we have is square wave. Can I make this better? I like this more. So like this, and then this, and then get this. Okay, so here we have a square wave. The square wave has an amplitude, as we know, a voltage. Now, on computers, let's say this is our binary value. So this would be on, geez, I'm off writing here, and this would be off. So yeah, so this would be on, that'd be off. So what happens is you have this rising edge. So you have a high level here. I'll change color. A rising edge here, and a falling edge here. There you go. Okay, I'm just going to redo this because it's making me mad. So here we have our on value, and for off, I'll just do it in black. Off. So now here I'll highlight. So this is right here is our rising edge. I mean, this is our high. I can't really rotate my image, so I'm going to write rise. And I'm going to write right here, I'm going to do falling. So fall. So these are the parts of a square wave. Now, ideally, a square wave never looks like this. So let's look at a real square wave. Oh, perfect, first search result. This is what a real square wave would look like on the actual oscilloscope. Or here, this is a really good square wave. But as you can see, even in this image, it's not perfect. A square wave is never perfect. We'll take another look here. Take a look at this one. Now this one right here, I mean, this is probably the closest you can get to a perfect square wave. But if this image wasn't Garbage Revolution, we probably could zoom in more and actually see the little ringing at the top of the square wave. As you can see here, this is a really nice image. I like it. It shows the square wave very well. Oh my Jesus. Who makes these stupid crappy websites? Okay, that's making me mad. I can't go to that website. So you see, it obviously has a rise time because there's a little bit of slope there. So we can look at here. This one, it's going through a very long wire. And the reason I know that is because see this ringing up at the top. Actually, bury up. We'll do the same thing we done last time. Nope. We would choose a red pin. So this ringing right here, 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 what this is caused by inductance. So what happens is you have a wire, and if you've ever done electronics 101, Here's circuit simulator. Actually, this is a really nice example, but that's not what I'm going to show. So let's have some input circuitry here. So we'll have an inductor, and we'll have a clock. So right here. So everybody knows what a clock is. Basically on-off signal 101010. Your clock for your CPU might be 3 gigahertz, which means it's turning on and off 3 billion times a second, which is truly amazing. So there's it took me a while to figure that out. Inputs out ground. Yeah, here we go. So here's a circuit. So I'm going to view that in the oscilloscope, and then I'm going to view this in the oscilloscope. So we're going to look at the difference here. So I'm going to not show current, I'm just going to show voltage. Oh, what the heck? Let's get rid of that. That might be why. Let's view this wire on the scope then. Oh, why is this showing current now? Well, of course it's not going to show voltage because there is none. I need a better circuit. This circuit's crappy. There we go, that's better. How's that? It's like a nice clean view. Let's see current. I kind of want to increase the resistance here to about. I don't know what a good current would be. It might be just the inductor I have because it might be really high impedance or something. I don't know. I want to get a nice little ringing effect. Oh, that's really close to what I want. Perfecto. And it's a little bit not close enough. There we go. So, can I make this bigger? Maximum scale, maybe. Okay, so as we can see, clear it, reset. So as we can see, here's our square wave in, and obviously it's a perfect square wave. Now here is our square wave that we could see. Now the 50 microhenries here, that's to simulate wire. A wire is made out of metal, so of course it will always act as a small coil in a circuit. And resistance here is to represent a logic gate, for example. So you have your logic gate, right? That resistor is your logic gate. So here you can see our clock, which is 5 volts, is being turned into this volt and turned into this waveform, which is going from 5 volts, 5 volts, 5 volts. Don't need to show current. And yes, trust me, that is 5 volts, as you can see the voltage meter right there. So it's going 5 volts back and forth, but where we have the inductor, we get a little bit of offset ringing, and it takes a while to rise and fall. So that's the reason we have problems with ringing and stuff. Now, that's not really related to Logisim because, of course, in Logisim, nothing takes current and everything's perfect waves, right? because that's how Logisim is. It's designed to be that way. So you can test your circuit in perfect condition, but of course, the real world is never perfect condition. The reason I was telling you that is to give you an idea of what you'd expect if you were to build this in your life. But as you can see, we're triggering this on the rising edge. We'll see the buffer also triggers on the rising edge. So that means our data from the buffer is going to be delayed, and it's going to only come on the high level. But we're triggering these registers on the rising edge. Instead, we need to be triggering these registers on the high level. So now let's try. So we'll do 8, set. So we get 8 because we're auto defaulted to pass A. We'll set 1, so that's going to pass B. So we'll set 4 as B. Boom. So that worked. Oh, hold on. And we'll set to our opcode to pass B. So pass B. And since B is 4, yeah, that's going to work. Of course. Makes sense. Now let's try them not codes. Now normally you wouldn't test it like this. This is just kind of really test. So we're going to get not 8. Which, look here. Yep, that looks correct. And let's clear these. Now let's try some. Let's add 2 numbers. So our add code was input, what? Let's say 7? Yeah, 7. Input 7. So we need to do 4, 1, 2, boom, 7. Those are opcode. So let's set our values to 0. Let's do 8 plus 8. Boom. Boom. Overflow. Oh no. Well, what that means is it's 16 because you know your 5th bit is 16. And because I showed you guys how an ALU works, we know their overflow is our next bit. So let's do 8 plus 4. We should get 12. Oh look, we got 12. I don't know. 8 plus 2, 10. 8 plus 1, I bet you can guess the answer. Of course, 9. 8 plus 12. Wait, 1 plus 12, 13. And so on. So we know that part works. And since we basically designed everything off that part, I think the next bit will be trying out to multiply some numbers. So that was 8, because it's 1 out of 7. So let's set our values here. We'll do 2 times 2. So we get 4, of course. 2 times 4, 8. 2 times 8, uh-oh. 0, what? Let's change our opcode to our carryout. Never mind, we got 16. Well, we got 1. And you might say, oh, that's not right. You shouldn't be getting 1. Well, you got to take in consideration that, let's see, do I have paint? I think this computer has paint. So, let's draw 2 squares here. Boom, and another square. Boom. So these are some nice squares right here. So now we get our beautiful brush here. So this will be our carryout, and this will be our sum. So our sum might be 0, but if our carryout is 0, 0, 0, 1, we take this, we combine the two to get 0, 0, 1, 0, 0, 0, 0, which equals 16. Yay! So 4 times 4 is, no, we done 8 times 2. 8 times 2 is, of course, 16. So that's how that works. Pretty simple, pretty straightforward. Good system. Now what I am going to do is I just realized the flaw in my design. I don't like that, since I kind of want this overflow bit here. I also add a start overflow. It means multiplication overflow. That's basically what that means. And we'll change the name of this to plus overflow. That's probably better in the long run because, I mean, it could be used in an instruction somewhere to get something important. Okay, never mind. Is there a way I could just do a splitter? I'm going to have to do an OR gate thing. I hate doing OR gates. They're ugly. And it don't matter the order these are in here because all we're doing is we're checking to see if one's on. And if one's on, well then we can do overflow star. Which makes sense. So our multiplication overflow, boom, we get a star overflow. Pretty simple. And might as well do a full star overflow. Full star overflow. Because heck, why not? It's not going to make the chip bigger, so there's no reason not to. And we'll make this 4-bit, of course. And it's going to get mad at us when we're testing it because, yeah, we don't like, for some reason, when you add in new components. So, now we got that. And all that. Now let's do the next part. Let's try a bigger number. 8 times 8. Boom. That's not going to be a good number, is it? And we get 4, which let's open up Paint again. 0. Oh my jeez, who even created that? Control A backspace, delete or something. What? So we got 0, 1, 0, 0 for overflow. And now let's go to our non-overflow. 0, 0, 0, 0. Now, we do a little bit of magic. So that's 1, 2, 4, 8, 16, 32, 64. So we get 64. Yay! So, I bet that's conclusive evidence our ALU works. And I'll make another part sometime soon. So I gotta upload this now.